where we can characterize materials up to nano level. And device characterization is specific to the application. So generally, whatever device group is there making the devices, they have the device characterization facility with them. The material characterization is a centralized facility. And now DRDO is the thrust is on productionizing through production centers and industry partners. As we are a semiconductor lab, you know till now, semiconductor industry is a very capital intensive industry. So you do not have a very big ecosystem of for semiconductors in the country till now. But with the National Semiconductor Mission, we are hoping that we will get enough semiconductor industries which can carry forward whatever we develop at lab level. So in the past, what has happened is whatever we have developed at lab level, if we have to deliver a certain number, we used to do it in the lab itself. But somewhere in the mid-80s, we started developing our own production center. Primarily, we have two production centers. One for 3,5 gallium arsenide, gallium nitride, which is called GATEC at Hyderabad. And then we have a center called StarC, that is at Bangalore, and it works on all the MEMS technology and other sensors. So these are our two production centers. And we have a very active interaction with academia. And now the emphasis from DRDO side is also that we have to interact with academia. So whenever we take up a project, we have the design and whatever academic can contribute, we are looking towards it. And the thrust is also that whenever we take up a project, right now, because we have to convert that whatever we have developing into a product, so we have to handhold the industry partner also right at the beginning when we conceive the project. So this is the model which DRDO is following right now and what we are also following right now. So basically these are our area of work. We are working in a variety of fields. We are about 350 scientists, 350 personnel with 150 scientists and 150 of technical staff. And we work in the area of RF devices, basically gallium arsenide, gallium nitride. And we start right from the material to the device to productionization at GATEC as I mentioned. And then we also work on optoelectronic devices, which are laser diodes, and also some IR detectors. And for realizing these detectors, whatever materials are required, that is the 3 arsenide, nitride, antimonide, we grow those using our own systems. Basically, we do a lot of epitaxy also, and we do some bulk growth also of semiconductors, as you can see. Then we also, another important area which we work are the sensors. So we have a variety of sensors which are developed based on the micro electromechanical system, that's the MEMS sensor, based on SAW sensors, and also acoustic sensors, and sensors based on carbon nanotubes. And for a variety of devices, we need a lot of cooling. So we have developed several cooling technologies also, Stirling cooler, JT cooler, and thermoelectric cooler. And right now we are taking up, for the last 3-4 years, we are working in both quantum technology and terahertz technologies. These are at the seeding stage right now. So these are some of the products which we have developed. Basically all are semiconductor products. So some solar cells, impact diodes, quantum detectors. These are, we can say the timeline up to 90s. These were what we were developing. And then we also developed some ferrite material and then phase shifters based on that. And they were productionized at Cell Sahibabad and they are used in the Rajendra radar. Now this radar is being phased out. So this technology is going out of production. And some of the products which we developed based on gallium arsenide, these are used for the space program by ISRO, which are being used in Cartosat, Trisat and all. And we also developed some laser diodes. For all these 3 arsenides, 3 nitrides, the production center is GATEC. And as I said, the cryogenic technology is the JT cooler, Stirling cooler and thermoelectric cooler. So we have also developed a variety of sensors based on different, and we have a number of facilities. We have a bulk growth facilities, we have germanium Joukowski, and we have Bridgman growth, and for silicon carbide, which is a technologically important material, we have a QVT reactor, and we have epitaxial growth facilities, that is MOVP and MBE. And as I said, the material characterization facility, the nano fabrication facility, and the semiconductor processing facility, and several test and measurement facilities as required. So coming to some of the advanced materials we have developed in the recent past. One important material which we have developed is the silicon carbide single crystal roll. Silicon carbide is a very important material. It's a wide band gap material with a very good thermal conductivity, and it is used as a substrate for all the 3-nitride epitaxy which we subsequently do. And right now we also have silicon carbide based power devices which are coming in for the EV applications. And these are the specifications. Basically, we grow 4-inch wafers, so we do right from the silicon carbide ingot. This is a very tough technology because the temperature melting point is very, very high, and to control the composition and the micropipe density across a 3-inch wafer, which has to be processed. We cannot afford any non-uniformity of properties along the wafer. So these are typically the specifications. And after making the ingot, we have the facility to slice the wafers and process it into substrates. So the lapping, cutting, lapping, polishing, everything is done at SSPL. And this is one technology which we have developed recently. And on this silicon carbide substrate, we have grown for RF electronics, algan based layers. And you can see this structure here, which is a hemp structure. And basically on silicon carbide, you have to grow different layers, starting from aluminum nitride to gallium nitride to aluminum nitride, again a spacer layer, for thicknesses varying from 2 micron to 1 nanometer. And all this is done using what is called, the technique is called MOCVD. I don't know if you've heard of it. It's metal organic chemical vapor deposition. And the challenge here is that each of these layers has to be grown at a different temperature. And you have to have very atomically sharp interfaces also. So these are the challenges. This material growth process has to be optimized. And then we have developed the device grade material. It is not as trivial as it sounds because it takes a lot of iterations and characterization before we reach there. And so then we can look at the on-wafer uniformity and run-to-run repeatability. And typically this is the AFM measuring the surface roughness, which is as good as state-of-art material available. Then we also have a molecular beam epitaxy. Why I am showing this slide is here you have to grow what we call superlattice layers, 3 nanometer, 0.3 nanometer, and 3 nanometer. And these have to be grown about 300 to 500 periods. This is a strain layer epitaxy in which the strain has to be balanced. So this is a challenge, and then you can see the TEM. You can see the atomically sharp interfaces, and the HRZ study characterization which we do shows enough satellite peaks which speak about the interface sharpness. So these are the requirements which we have for these materials. Coming from material to technology, basically GaN technology is a very important technology we are working on. This basically is a wide band gap material which can be used at high temperatures and high frequency applications. And this is a challenging technology in the sense that once I have grown the material, I give it for device fabrication. A number of process steps have to be done before we realize. Here you can see the wafer. This is the process wafer. This is a full 3-inch process wafer in which these devices have been fabricated. This is one technology process which I would like to draw your attention. This is what is called basically a via hole. This via hole has less than a micron dimension, and these have to be, basically the substrate is about 300 micron, which is thin, lapped down to 100 micron, and then you have to make these holes, keeping the geometry intact. So this is the kind of work you have to do when you come to a semiconductor plant or a semiconductor industry. So this is a very challenging process, and then you also have, when you make a circuit, it's not just a hemp device, you have to have a inductor and a capacitor and a resistor. So all these have to be designed and put in place so that you have a MMIC wafer like this. And these are some of the devices which we have grown: a power amplifier, a low noise, and a switch. All these three are designed so that in combination circuits are designed and you have what are called the MMICs. These are GaN-based MMICs which have, this is for example one C2KU band. These are very important and useful for radar applications. basically the advantage of gallium nitride is compared to what we have today, the size of the radar comes down. So the weight also comes down, and because of which it can even be put on an aircraft. What we call the ISR radar, actively electronically scanned radar. So this is for that application, and these are basically not available to us in large numbers from anywhere, so they have to be developed indigenous. And then we also work on gallium arsenide based laser diodes for various defense applications. And depending on the user requirement, we have to make them for different output power in different kind of packages, and even for fiber coupled laser diodes as required by the user. So all this is you can see some of the applications for detonation and for the pumping of other lasers which can be used as direct energy weapons. So these are the requirements. And again, the pilot production for this is gated. So this is typically a process for a laser diode. So you have to have, for instance, in a GaN, you have a 17 mask process end to end before you get the circuit. So all that has to be done. So similarly, this is the typical process fab sequence for the laser diode. So you have metallizations, you have mesas, you have anti-reflection coating, you have passivations, and then you have your cleavage to form the cavity, and finally you get your laser diode. Then we also are currently working on blue-green laser diode technology. This is under development for underwater application. So then we also work on a number of sensor technologies. So these sensors are based on the micro MEMS, that's the micro electromechanical systems, and these are again used as fuses, electronic fuses in the place of mechanical fuses, and these are highly in demand, and they are very miniaturized, and they are again, this technology we productionize at a place called StarC. We have a center where all our MEMS technologies are productionized to supply in the required number for our users. Then we have acoustic emission sensor. These sensors are used for avalanche prediction so basically this is the sensor. So the sensor and the sensor system, these are based on piezo composite materials. The sensors are made and packaged as per the user requirement, and they are deployed in high altitude. Because we want to do avalanche prediction for our defense forces who are deployed in the high altitudes. So now this sensor system plus the data acquisition system, because the sensors are placed where the avalanche is expected, and then you have to generate a lot of data. So these are placed and data is collected throughout the year, and this is then given to the user, who then develops a model for avalanche predictions. So this is one technology we have been working on, and as a consequence of this, we are also working on landslides. So this is also one technology we are working on. It's a similar principle, the design is different, and the same thing that you have to place your sensors at vulnerable areas and collect enough data so that you can develop a model for prediction in future. The model is not our job, we basically develop the sensors. Sensor and the sensor systems. Then we have several SAW-based sensors also. We have what is called the INASICA, which recently has been qualified for chemical warfare agent detection and for toxic gases also. And then we have SAW-based signal processing devices. And then one wireless passive physical sensor. This is very important because there are several places where you would like to know what is the temperature during operation. So when you have a temperature, suppose you have a turbine rotating at very high speed and you cannot place your sensor there, you need to have in a wireless mode. So this is a possible solution which we have taken up recently. And basically you have the sensors mounted on the wherever you want the temperature during operation, and then you have an interrogator unit which sends a signal and you can collect data so that you get a real-time picture of what is happening while the system is operating. This is basically the same thing. And then we have a CNT-based chemical sensor. CNT work was done about 7 years back, and based on that, some sensors have been developed for chemical for detection of ammonia and NO2. And this has been now tested, and we have made the prototype, and this has to go for, it has been given to some users so that they can test it out, so that again the fabrication of this we are now doing at Stasi. It is not yet started, but this is what we plan to do. Then recently we have 3 years back we have started this terahertz and quantum initiative. So we were talking about again we have a MEMS-based terahertz detector. We have just developed the single element detector. Basically, it's a metamaterial based detector. The metamaterial has been designed and fabricated, and the device has shown terahertz response. So now we have to go in for an array to make the actual device, and then go for the optics and so on to make the complete subsystem. Then for terahertz sources, you have a broadband photoconductive material which can be used as a source of terahertz, and it also can be used in the detection mode. So for this, we had to develop a special material which is called the LT gallium arsenide and indium gallium arsenide. So this material is not available to us from anywhere. So this is also done in-house, and we made this. We are now in the process of developing. This work is still going on. Then zinc telluride is another terahertz material which we are working on, again for terahertz transmission and terahertz detection purposes. And our material has been, there is a very active group at TRFR which has been working in this area. So we have given our substrates to them, whatever we have developed. They have tested it, and now they're in the process of developing the complete terahertz system for imaging using this. Then graphene based also some terahertz modulator and detector has been developed. This has been demonstrated. Now we have to work further to develop the systems. Then there is a quantum sensors initiative also. Basically, we are working on 2 applications, which is the ultra small atomic clock and magnetometer. This is for providing wherever there is no GPS, you need to have the communication. So the atomic clock is targeted for that, and magnetometer for underwater application for detecting the magnet. Basically, ultimately for submarine detection. But these are at the nascent stage, and when the concept is there and the design is there, but when we are actually executing it, you see that there is a lot of gap in the electronics which we need to develop, and so that is what we are right now looking at. So these are some of the things which may be of interest to all of you. So if you want to know basically how DRDO is interested in working with the academia, right now there is a strong thrust on DIA COE, that is the Defense, Industry and Academic Centers of Excellence. About 15 of them have been opened in various IITs and ISC, and you can look at our website on a range of technology. Basically, the idea is to build multidisciplinary collaborative teams for development of advanced technology for futuristic defense. So they want the student community, the academia, the niche technology industries, they have to come together to provide these solutions. And the other way in which you can, academia can collaborate with us is through our directorate of ER and IPR, in which basically you submit project proposals and they screen them for the application to defense. And then if they get through the screening, then they are sent to the domain lab, whichever is interested, and then they are evaluated and processed for further sanction. Then apart from ER, IPR, we also have 4 research boards: aeronautical, armament, life sciences and naval. You can just go through the website and you can see where, whatever work you are doing, where it fits. And then there is another mode in which basically this is initiated at the lab, like we initiate this. Suppose we have a project and we have a need, we have a gap somewhere which needs to be filled, knowledge gap or technology gap. then basically how we go about it is we look at literature and look around us and see who has some experience in this field. So then we contact them and then try to take proposals from them, have discussions with them and see if they can be of help to us to fill that knowledge gap. So most projects now we have 1 or 2 CAST proposals right at the initial stage before the project is taken up. This is planned and we have several CAST projects now, about I think about 30 of them going on, and we have successfully worked in this mode with academia, and basically for, like I showed you the T2SL and the HEM structure simulations, we have a QCL structure which needs to be simulated. So for simulation we need the help of academia, and also for computational and thermal management and so on. And we have also worked for process development. Suppose there is a gallium nitride and we need some etchant. So that problem somebody can take up and develop the etchant with repeatability, with the surface characteristics we need and so on. And some even metallization schemes. So it depends on basically what the researcher brings to the table. If it is of interest to us, then we have very active interactions with them. And this is all basically. One thing I forgot to say here is that we have a very active students training program. So if anybody wants to work here, I would recommend at least 6 months of training. If you can take, you can work in any of these areas. You can approach SSPL, and we are open to providing that. Thank you.
Thank you very much, Madam Padmavati. Yeah, it was a brilliant lecture. So the lecture was basically it was on advanced semiconductor materials and devices. But the way that you have covered the various aspects, starting from the basic material, then the sensors and the technology and everything, I think it was completely a complete lecture. And moreover, the last part I like the most, where you have focused the interaction between the industry and your institution. And moreover, you have mentioned that how the different, even the student, they can take benefit of the different initiatives. Now, once again, I thank you, and I would like to join me thanking Madam Padmavati for giving the lecture. The floor is open for 1 or 2 quick questions. Any question, relevant question? Yes.
We are from Kolkata, and we have one electronics and VLSI technology department. Actually, where we have once developed one fabrication laboratory regarding process and others that you are talking about, and we have synthesized one perovskite material also and studied some like JCPDS data like XRD and others, and we have seen that it is very good material. It has been tested. But for other study, that absorption and other kind of study, we cannot go beyond that because we have no such facilities here. And with the university infrastructure, the university is not providing us that kind of facility. But students are very interested, and we are also very much interested to give that human resource that are demanding, now nations are demanding semiconductor facilities.
What is your question?
Now my question is whether you are giving support to this kind of
if any characterization facility is available at SSPL, you can definitely write to the director, and we actively support any thing which we have. If we have the facility, then we can work out a schedule and you can come and plan it with the relevant groups.
Okay.
So you then first you can write to the director, and then she will redirect the mail to the concerned people. So then the interaction can start. I mean, there is nothing which we don't do. If the requirement is there, we can always do.
Then you can submit some proposals also for this proposal.
Project proposals, if you want to submit, it is through the ER and IP mode. So you just go through the website, as I said, and then there are forms are also available. So you can just have a look at it, and you can send the proposals to ER IPR, and they will just have a look at it. As I said, ER IPR basically looks at if there is a defense application. So then they redirect it to the whatever domain lab. So that is how it works. Okay, funding is there. So, but you have to go through the process.
Thank you. Thank you.
And whereas Madam very clearly mentioned that it is better you go through the website because the time is very limited. So my point is that if you have any question relevant to the lecture, please come forward. No question. Once again, I request to join me in thanking for Madam. I invite the next speaker.
Thank you very much, ma'am. I request the session chairperson to kindly present the memento to our speaker.
Okay.
Yeah, may I invite the next speaker, Professor Chaplov from Mumbai. Unfortunately, I don't have any CV of yours, so I will request you please introduce yourself for 2 minutes. Please. Okay. Yeah.
So what we can say about our next professor, Professor Samantlal Chakon. Let me give you a brief introduction about him. Professor S.L. Chaplot is an INSA senior scientist at Bhabha Atomic Research Center, Mumbai. Earlier, he was director of the physics group at PARC. He is an elected fellow of the Indian National Science Academy and the National Academy of Science, an academician in the Asia Pacific Academy of Materials. He was selected as an outstanding referee by American Physical Society. He received the DAE Homi Bhabha Award for Science and Technology. He served as the president of the Indian Physics Association and the president of the Neutron Scattering Society of India. Let's put your hands together for him.
Yeah, thank you very much for this invitation. And I will be talking about dynamics in battery materials. Okay. Yeah. Okay, I have several colleagues at the ARC, and as you notice, we interface between theory and experiments. Our previous speaker strongly advocated that, and in fact, I really support him because unless you join the two together, you live in isolation and you cannot go very far. We have done experiments, we have facilities at the Bhabha Atomic Research Center and also some other neutron scattering centers. So, let me introduce the issue. Can you do next slide? Then I'll use this. Next is right? Fine. Is it good? Just the previous one. Or the previous one? Okay, now the subtopics that we work on and which is Well, all right, don't worry. I think let's take it on. So the subtopics we work on are, you see, dynamics in solids. There are two kinds of things. We have periodic dynamics like phonones, etc., and we also have stochastic dynamics like diffusion. Okay, and so we primarily use the technique of neutron scattering. Uh, there are two varieties: inelastic scattering and quasi-elastic scattering. That refer to, and you can see the periodic dynamics as a large variety. And now, because these are so complex in complex structures, you heavily depend on computational models of the dynamics. Yes. Okay. So, inelastic scattering is used to study periodic dynamics, and quasi-elastic scattering is used to study. And the kind of things it has is phonon dispersion relations or diffusion and data analysis are done by lattice dynamics and molecular dynamics. To go a little further, so neutron scattering is like Raman scattering. Essentially, what happens is you have an incoming radiation, you have a sample, and you have outgoing radiation in different directions, and you look at the energy and momentum conservation. So, like in Raman scattering, the radiation energy changes, and the change in energy is related to what excitations we are talking about. And similarly, there is a change in momentum. In diffraction experiments, for example, this is very different. So, what you need to really look at it is the change in energy and momentum of the neutron scattering, neutron radiation, and that allows you to study the dynamics. Okay, just a little bit more. So, if you plot, for example, how much the energy of a neutron changes against the intensity of this process, then at like zero energy transfer, what you essentially have is a diffraction, and this kind of thing we use to study the structure in crystallography. If the elastic line is broadened, okay, there is some resolution of the instrument, so there is certain width of the elastic line. But if there is a further broadening, then this is related to stochastic motion. So if you have, for example, diffusion of atoms in a crystal, then that would give you broadening of the elastic line. Okay, and the width of this is related to the correlation times, or so can be related to diffusion coefficients and so on. We will just show that. And like phonons or other excitations, they show up at finite energy transfers. You have processes like energy gain and energy loss, very similar to what you have in Raman scattering. So very similar to the Raman scattering, you can measure excitations both with energy gain of the incident radiation or energy loss. So this is just the basics. I don't get to just into. Now here, because in battery materials, our focus is on ionic conductivity, and ionic conductivity is determined by diffusion of atoms. Now, diffusion, as I said, we can investigate by quasi-elastic scattering, that is the broadening of the elastic line, how it changes as a function of energy and momentum. And the quantity that is measured is what is called the dynamical structure factor. It is simply the probability of scattering as a function of change of the momentum and change of the energy. Okay, this is h cross q will be the momentum and h cross omega will be the energy. Okay, and so here again there is certain elastic part which is due to the time average structure, and there is a quasi-elastic part. So the broadening part, we fit it with a Lorentzian function. Okay, so if you fit it with a Lorentzian function, then this width of the Lorentzian can be related to the different kinds of modes of the dynamics. So this is a fairly involved process, but well, I don't have to bore you with all that. I mean, just to give a flavor that these are the kind of things that are done. So you do the fitting and so on. And then the width of the Lorentzian function, that is the width of the broadening of the elastic line as a function of the momentum transfer, can be related to certain models. This is one of the simplest models that gives you what are, for example, in crystal lattice, atoms don't diffuse exactly like a liquid. They may be jumping from side to side, and there is certain time it takes for jump and so on. So typically one can think of a jump a time residence time between two jumps. How long the atomic state one place on the average? This is stochastic. So these are not fixed numbers, and then the diffusion coefficient can be found by substitution. So this is one of the simplest processes for models. Okay. Now coming to certain specific aspects. So we are interested in lithium or sodium diffusion. So for lithium, you are very well familiar with these are the lithium batteries are used, and right now what one is interested in whether you can improve upon the solid materials. Maybe lithium in a liquid state would be different, but then solid electrolyte is something that is a focus on, which are more convenient to handle, and there are certain advantages. So, and alternatively sodium, because lithium again is in short supply and has its own problems, and sodium is abundant. So there is a focus on sodium battery materials. Okay. Now, but as basic scientists who are interested in the atomic level understanding of these materials, what are we interested in? Okay, crystal structure is one that crystallographers can look at and so on. What we are looking at it is the diffusion pathways and time scales. So within a given crystal or within a given solid, what are the diffusion pathways and what are the time scales at which the diffusion processes take place, and how this can be beneficially improved upon for practical uses. So this is what is eventual aim is. And then you can very well imagine that you are looking for low energy barrier diffusion pathways. So, you know, if the energy barrier for diffusion is small, then those will provide those preferential or preferred pathways. And that is what we would like to find out within materials. And so these can be helped in various ways. The structural topology, I'll take an example. And the point defects are useful because the vacancies or interstitials, they help in diffusion process. Another important thing is if you have an amorphous kind of structure, that has its own benefits. Then the other aspect is whether you can flex the host lattice, the host crystalline lattice, by some stoichiometric engineering or diffusion methods. Then one of the things, a couple of things that we found is that in certain materials, if you have polyhedra, some groups like SiO4, these, so a lithium sulfate, for example, or lithium phosphate, a polyhedral group of atoms like PO4 or SO4, its rotation is coupled with the translation of lithium atom, and so that is called a gear wheel mechanism, and that kind of thing helps in diffusion. Okay, then it is also found that the low energy phonons, you have in different structures depending on how the structure is engineered. You may find that there are very low energy phonons associated with the diffusing atom, lithium or sodium atom. As I said, it's not a liquid-like diffusion. So, for most of the time, the atoms are located at definite sites and they jump over from side to side, and that is how the ionic conduction or diffusion takes place. So, low energy phonons, and the eigenvector of these phonons may be related to the low energy diffusion pathways. And moreover, the softening of the phonons, that means the reduction in the phonon energy, or the phonon frequency as a function of temperature or thermal expansion or by other means can be supported. So this is the broad outline. Now let me take a few examples that we have investigated. Okay, over the last few years, or couple of years, we have looked at materials like sodium aluminum silicate or lithium aluminum carbonate. These experiments were done at the Oak Ridge National Laboratory, and we have done all the. Okay, see, what the way we operate is that we do certain preliminary work in our center, and we propose experiments to these advanced laboratories, and we get the beam time. Then we can use it and then get the data, analyze, compare with our models for the computational calculations, and then try to get the things out of it. Another is the amorphous materials. As I said, amorphization also helps. Then there's one recent paper that we have published is in a sodium zinc gallium sulfide material, where the topology of the structure is found to be very suitable for diffusion. Okay, then there are some papers recent on phonon related aspects. These same technologies are also useful for example, solid oxide fuel cells, where the diffusion of oxygen atoms is very important. So, fuel cells can be okay, so the first example I will take is lithium silicon oxygen. Okay, there are some experiments done at ICIS, that is a Rutherford Appleton laboratory in Oxford. And what is known is that the crystalline material does not exhibit diffusion, but the amorphous material shows diffusion at some higher temperature. And then it's on further rating, it transforms to crystalline phase. So what we find is that amorphization enables the lithium diffusion. It's a recent publication. Okay, so this is the phonon density of states. Okay, the neutron intensity. It's not exactly neutron intensity, but converted into the density of states as a function of energy. And you find that normally we are familiar with the omega square kind of density of states or E square kind of density of states. But then this is not just the acoustic region, some optic phonons come into play. And here, at room temperature, you have certain density of states, and then as the temperature is increased, there is a shift to lower energies in this material. Okay, but this is marginal amount. Now, if you go to the amorphous structure, then there is a lot more shift and a broadening. So, qualitatively, one can associate that the softening of these low energy phonons, and we can find out from theoretical calculations what is involved in these phonons. Okay, what kind of atomic dynamics or atomic motions are involved. So, this is through the theoretical calculations that, for example, the mean square displacements due to phonons have these components. So you have a large component from lithium atom. This is the same energy I'm talking about 5 to 10 billion electron-volts. So lithium has a large component, but then sulfur and oxygen also, silicon and oxygen also have a large component. And as we see by more detailed analysis, that this SiO4 interpolyhedral dynamics, lithium dynamics, that occur. Okay, this is data of the quasi-elastic neutron scattering. So the elastic line, we just shown the tail part of it. So you can see that with the increase in temperature, this is at low temperature you have only the essentially the resolution of the instrument. As you increase the temperature, there is a broadening of the elastic line, and you have some kind of increase in the intensity also because of phonons, but that can be accelerated. So this is fitted to a Lorentzian kind of function, and this width of this Lorentzian function is plotted as a function of the momentum transfer. Okay, and then this is fitted to certain kind of models. So what this essentially tells us, so this process, you can identify that there is diffusion. You cannot still identify which atom is involved because purely experiment will not tell you that. Okay, for that there can be other methods, experimental methods, but what we have done is through simulations, and then you can find out what. So, for example, the typical average jump length of the lithium atom is. So the jump length is typically 4 angstrom, which is related to some kind of particle distance, and there's a typical jump time of maximum picoseconds. There is certain diffusion coefficient. Okay. Now you can also, for example, simple calculation, molecular dynamics calculation. You can calculate uh, the mean square displacements of atoms. So in a crystalline material, the mean square displacement does not change with time. So these are just the phonon vibrations. So the mean square displacement is practically independent of time, and it increases with the temperature. So but this does not indicate diffusion. However, if the mean square displacement increases with time, this is a molecular dynamic simulation, then that indicates the diffusion. Okay, so in this amorphous material, and the diffusion coefficient is just proportional related to the slope of this function, that is this one. So from that one can identify this. Then the another quantity that is calculated is what is called a self-correlation function. So it's a correlation function between a lithium atom at a given time and at a future time. Okay. So if you calculate that, so in a crystalline material, what you find is that there is just one peak, and so they typically, let's say, half an angstrom, and this is related to just the mean square displacement phonon kind of vibration. However, in this amorphous structure where there is a diffusion, the self-correlation function shows first develops a second peak and then further broadens and so on. So this indicates how, as a function of time, the atom is jumping from an initial site to another site. So that's one can look at it. Okay, then of course from the theory or simulations, how much time do I have, sir?
You can continue.
Okay, fine, thank you. You can stop me anytime. So, if in the molecular dynamic simulation, as you know, you calculate the trajectories of atoms as a function of time, typically in the order of picoseconds. And then, if you look at this, then, for example, in crystalline material, the atoms are located at definite sites, whereas if there is a diffusion taking place, then this will not be so. So these are just the probability isosynthesis propagated. Incidentally, the temperature has to be very high because in a small simulation, see, in the real world, you can go up to seconds or minutes and so on. But in simulation, the typical time at which the atomic trajectories have to be calculated has to be a fraction of a picosecond. Okay, and precisely for that reason, but if you increase the temperature, then you can accelerate the process. So, I was just artificially done. All right, so this way one can identify or calculate what are at the microscopic atomic level, what exactly is happening. Okay, then if I look at, for example, just pick up one atom and see how its root mean square displacement is changing with temperature, then in crystalline material it is a constant. Here, this is the displacement from the original position. So you can see that it shows some variation, then it shows a jump. So this is like a jump dynamics. Okay, and whereas in amorphous material is more a mix of jumps as well as a liquid-like continuous process. So this is the microscopic understanding. And if you do the latest dynamics calculations where you can calculate the phonons and phonon eigenvectors, then you can identify specific phonon eigenvectors for different phonons. Let's see how what kind of dynamics is taking place. Okay, so what have we learned from this essentially is that the molecular dynamic simulations revealed that in the amorphous space, you have different orientations of this silicate polyhedra, and there are also several accessible pathways opened up for sodium diffusion. This is not available in this crystalline material due to definite fixed orientations, so we are not able to see it. I'll take another example recently we have worked on, that is the diffusion in this specific material. So this has not too complex a structure, but what we found, and here you have again this polyhedra, zinc sulfide or lithium sulfide and so on. So there is a network of this polyhedra, and the sodium atoms occupy certain positions. These are in the crystal structure. There are definite Wyckoff sites. 32G means in the unit cell there are 32 positions available, 16 positions. So a large number of positions are available in this structure, and so this is the broad structure. Okay, and we are trying to see what kind of features can identify the diffusion process. Okay. So first, these are the phonon density of states measurements as a function of temperature. And what we essentially see here is that the phonon peaks broaden with the increase of temperature. And the broadening is like, if you have harmonic phonons and this anharmonic interactions lead to broadening of the phonon structure. Then further we found that and through calculations you can identify what are the different components of the phonon density of states. This would be called the partial phonon density of state, which are atom specific. So the different atoms in the material, you can see what are the contribution to the phonon dispersion curves. The different atoms. Okay, sodium, selenium, gallium, and so on and so forth. Okay. What we identified here is that the key phonons where the significant broadening takes place are associated with the sodium atoms at of one type, 32G, that means we just call sodium 1 and 2. So that has a large broadened structure, whereas the other one has very sharp structure. And then these are calculations of the mean square displacements again, which tell us that the sodium of the 32G side has a large component at this low energy, where this phonos, low energy phonos are. And okay, the other kind of measurements, the quasi-elastic neutron scattering, we do see the broadening as a function of temperature. And then this again, the broadening of the elastic line as a function of momentum transfer is plotted. This is experimental data from the Oak Ridge National Laboratory. And we can also have corresponding calculations from the ABV-IIITM molecular dynamics simulation and corresponding. Okay, so this essentially helps in validating the simulations, and then we use simulations for more detailed understanding of the underlying microscopic physics. Okay, so what do we see here now? Again, but here again, you see in the real structure, the diffusion is helped by defects of various kinds. In a perfect crystalline structure, it's more difficult. So we have introduced some small vacancies, and that allows us to identify the diffusion, which you can see through the how the mean square displacement increases with time. We show the diffusion. If you just look at this, you may feel it's like liquid-like, but then really it's not liquid-like, but strongly influenced by the underlying lattice. Okay, this is again the distribution diffusion. Yeah. So, okay, what did we discover? See, we plotted the probability density of the sodium atoms, which are initially located at one of the two sites. And then we find that this there are definite pathways in the structure which are connected, and the sodium, this particular kind of atoms, they diffuse through it. So, whereas the other kind of atoms, that is the 16F, they don't have such kind of diffuse pathways available. So, in fact, what we therefore said that this is the topology of the structure is such that enables certain pathways, and then these are you can say some kind of a zigzag chains of the sodium atoms in a plane, and they also have atomic diffusion or jumps across. So this is the AB plane in the crystal structure, and if you project the BC plane, C is along the perpendicular direction. So these chains, there are also jumps between the chains along the C direction, and so this way we have identified what are the pathways and what is the topology of the structure that helps in the process. So in other materials, if you can identify this kind of topology, that would be helpful. Because these are again detailed snapshots of how the jump dynamics takes place and what are the time scales. What of studies done this way. Okay, this is again the self-correlation function that tells that how, for example, as a function of time, the second peak develops. So, the first peak, this is the correlation, self-correlation of the atom as a function of distance from the initial position at zero time. So, in the beginning, you have just the phonon kind of vibrations, and as time proceeds, the atom would have jumped to another site at a distance, and then so it is the same atom at a later time is then located at a different position again. So this helps us to identify what are the jump lengths and jump times in this process. Okay, so now this part of the talk, there are two things that are identified. So in the amorphous structure, due to the shallow free energy landscape, attributed to random arrangement of Fourier units with large number of local minima, that's we can copy. And in the sodium, the second material, there is structural topology of the sodium atoms in zigzag chains of the certain sites that provides the pathway for sodium diffusion, and the diffusion is enabled by soft channels. Yeah, how much time, sir? Okay. So, in no further time, I will jump over to this another example and just go to the. Yeah. Okay, so just to summarize, okay, we have looked at the diffusion pathways and time scales, and the structural topology and point effects, those are available. Then the stoichiometric engineering can help in identifying the diffusion processes by fixing the status, couple dynamics, and the low energy phonos. Okay, with that I will. Thank you.
Thank you, Professor. Applause.
Yeah, thank you.
It was a fantastic lecture. It started with the energy devices, with the simulation of the experiment. For me, the beauty of this lecture is the physics and the atomic dynamic characteristics of the solid state material, which you have covered very nicely. I am not from the field, so I don't want to draw myself into this. So I will throw for the question. But any relevant question to the lecture, no suggestion, nothing like that. The direct question, please.
Sir, we are not actually having this kind of lecture, but it was so fascinating. And I was involved in charge carrier transport in Gwalior and others. And I am trying to correlate with the molecular dynamics what you have, because we have done also human scattering and others. So my question is, when you are deriving the time, it is a time-dependent Schrodinger equation. You have this kind of energy eigenvectors were very much solving that eigenvectors you are giving. Is it like that? And the flow is completely, the molecular flow is happening naturally in the battery materials.
Yeah, there are two things. The first thing is if you want to calculate the phonon spectrum, there are standard techniques of lattice dynamics. Okay, so that is how you calculate the phonon dispersion curves and related properties. Okay, that's one. And second, diffusion, yes, it's a molecular dynamics. The name is molecular dynamics, but it's only solving the Newton's equations of motion. And so that in a density functional theory calculation, the forces between atoms you get through the density functional theory. But you still, once you got the forces, you are solving the Newton's equations of motion for the atoms. Okay, and that allows you to get the how the atoms move as a function of time. So whether they're just vibrating about a fixed position, or they're jumping from side to side, or in a liquid, how they move, what kind of pathways to take. So this is what molecular dynamics can do.
And the harmonic, that the phonon we can
Phonon you can
assuming that it is
calculate.
harmonic, it is not always harmonic.
Yes. So if you do a molecular dynamics calculation, then there is no restriction like harmonic, because you are actually calculating as it is, and from that you can do some Fourier transforms, etc., for the position time, and get your phonon structure. That is that will include both the harmonic and anharmonic interactions. Okay. So molecular dynamics, there are certain limitations about how many atoms you can take and so on, but it's a well developed technique to calculate phonon spectrum also, including at a finite temperature, including harmonic and anharmonic terms, and also look at stochastic part of the dynamics like of total systems.
Yeah, very illuminating and insightful talk. I mean, the means by displacement versus time, I was just wondering if you have considered calculating the diffusion constant from Einstein's equation. So, it is the slope of the means by displacement versus time.
Yes.
That's getting
So you can get diffusion coefficient many ways. One, the Einstein relation, just a slope. Other by this, if you go to details, the position time correlation functions. So you take the jump times and jump lengths. Third is if you calculate the velocity autocorrelation function, and then the Fourier transform. At zero energy, you get a component which is very different. So there are three different ways. Okay, and that will, if you can, we have calculated the whole three methods, try to see if there are differences or not, and if yes, then both they might be related.
Yeah, please.
So very interesting talk. So the last, I have two questions, but I'll ask one question. The 32G side is basically solved for non and diffusion faster than 16F.
Yes.
But if I look at the near neighbor distance in phonons, it's the other way around. 16F has 4.2 angstrom distance. So educated guess is going to be if you have a larger space.
True. So that is near neighbor distance is not sufficient. One must look at the structural topology, how the atoms are located. See, suddenly you can imagine these are not the first neighbors. In between you have these polyhedral units, and so details have to be seen. Moreover, in these structures, you have just only one first neighbor or one second neighbor. There is a distribution, and so you calculate the pair distribution function to identify what is the distribution and so on. So,
Yeah, because I thought its bonding
but
is
it's
stronger.
very important.
Yeah.
That's just looking at the crystal structure, you cannot jump to a crystal.
Any other question, please?
Sir, in one of your slides, I've seen the soft mode of phonon. Does soft mode phonon means imaginary frequency?
No. Imaginary frequency would not be soft, it will be unstable. Okay, because if a imaginary frequency, if you write e to the power I omega t, and if omega is imaginary, then it will become e to the power minus omega square t, minus something t. So that phonon will simply decay, it will not be stable. Okay, so imaginary frequencies refer to unstable vibrations. They are not stable vibrations. On the other hand, soft phonon just means, crudely speaking, very low frequency, but strictly speaking, there are phonons which change, decrease in frequency as a function of temperature, for example, and then eventually can lead to phase transitions.
Yeah.
Okay, so but soft phonon means soft means very low frequency.
But under some kinds of perturbation or maybe some kind of strain that may be transferred to the imaginary.
No, then so if that situation is about, as I said, for example, in strontium titanate or many second order phase transitions, the frequency will decrease, and then when it's approaching zero, your phase transition takes place. So if you still calculate beyond the phase transition, then it will give an imaginary frequency. Okay, so imaginary frequency would be in the unstable structure, but and that structure would then transform to a stable structure which may have a lower symmetric frequency. Like the cubic strontium titanate transfers to or barium titanate, say to a tetragonal structure or orthorhombic structure or rhomboidal structure. But the cubic structure has an imaginary frequency, but not the. So once it becomes tetragonal, then it's no more imaginary.
So one thing I want to.
Yeah, please, sorry. Professor Chaplain is around, so you can discuss the matter with Professor Chaplain during the coffee break or during the lunch hour. Because of the time limitation, so thank you very much, Professor Chaplain. Please join me in thanking
Thank you very much.
We would also like to present a memento to our honorable speaker. Thank you so much, sir.
Thank you, Professor Chaplain.
And for our next speaker, I would like to invite Professor ABV-IIITM to speak on the topic BMT perspective of electronics, piezoelectric, and about his biography. I would like to say, after having completed his PhD, in 2004 from the Shah Institute of Nuclear Physics, India, Professor D. Sarkar had his first postdoctoral stint at the Fritz Haber Institute of the Max Planck Society Berlin, Germany. And the last one at Uppsala University, Sweden. In between, he served as a research scientist and engineer on a visiting investigative program between CENES and CNRS, France. And ASCA Singapore, he has been recipient of the President of India, Medal for the year 2000. Up to the date, he has published more than 1,000 papers. He has guided
100, not 1,000.
more than 100 papers. He has guided 5 students
Yeah, yes. That's my mentor.
to the successful completion of their PhD and mentored postdoctoral fellowship. Please put your hands together to welcome them.
So IIIT in Gwalior is a second home to me. Professor Anurag Srivastava is a wonderful host. It's always great to be here, and I thank him for the opportunity to showcase our research findings at this wonderful international conference. Okay. So this is the title of my talk as she read it out. Okay. And so first of all, I would like to acknowledge my group of PhD students, both past as well as present, because today I'll be presenting the work done exclusively with my PhD students. Neelkant Tripathi is standing next to me. This picture was taken on his birthday, and he is here in the audience, and he will be presenting a poster. The cake is missing in the picture. I'm sorry for that. So, apart from the pursuit of our independent theoretical research, we also collaborate with experimentalists, and we provide them with a strong theoretical support. So, if time permits, I would like to touch upon some of our such collaborative work, where we have provided theoretical support to experimentalists. Okay, so this is how the talk came organized. So broadly speaking, we pursue research on 2D materials for different kinds of energy conversion and next generation electronics. So I'll start off with valleytronics beyond single layer MS2, which will be followed by the theoretical predictions of these monolayers for flexible piezospintronics, and then piezoelectricity in a few selected monolayers and van der Waals heterobilayers will be covered in this talk. And serendipitously, we have come across an ohmic contact in this van der Waals hetero bilayer. That will also be, I'll also talk about that in this talk. Okay, and the workhorse, which has been employed in our scientific computations, comprise of density functional theory based approaches as implemented in class. So, as we are all aware, novel properties arise at the nanoscale, which are usually non-existent in the bulk form of the materials. We can use molybdenum disulfide, the most widely studied two-dimensional semiconductor, as an example to understand that. So, molybdenum disulfide comprises of a multi-layered van der Waals solid, and when it is thinned down to the level of a monolayer, so as we are moving from the bulk to the nanoscale, several interesting properties arise, like this and that. So, but we are particularly interested in this one. So, as we are moving from a bulk multi-layered van der Waals solid MOS2 to a single layer MOS2, what happens is that this point group symmetry changes, the symmetry is lowered, the inversion symmetry is broken, as a result of which piezoelectricity as well as valuetronic properties arise in single layer MOS2. Now, theory has preceded experiments in several instances, including the prediction of piezoelectricity in two-dimensional materials. Piezoelectricity in two-dimensional materials was predicted, was in this paper, was discussed in this paper, in this JPCL paper in 2012. And then in a few years down the line, it has been observed and confirmed experimentally in these two papers from the Nature group. And the origin of piezoelectricity is the broken inversion symmetry. So as you can see, this is the supercell of MOS2. Here the two atoms are different, so the inversion symmetry is broken here. Therefore, it shows piezoelectricity. And however, in graphene, both the atoms are the same. The inversion symmetry is present in graphene, therefore, it doesn't show any piezoelectricity. And experimentally, it has been demonstrated that molybdenum disulfide containing odd number of layers show piezoelectricity. However, MOS2 containing even number of layers, the inversion symmetry is present in it, and therefore it doesn't show any piezoelectricity. So only odd number of layers of MOS2 exhibits piezoelectricity, not even ones, due to the occurrence of inversion symmetry in it. And likewise also, the single layer MOS2 shows these valuetronic properties, Valley Hall effect. I'll be talking about that in the next few slides. The bilayer doesn't show. As you can see here, the bilayer, the curve is, the Valley Hall voltage is flat. It doesn't vary with the voltage. Now, apart from the charge and the spin degrees of a freedom of an electron, another degree of freedom arises in a single layer MOS2. As you can see, the inversion symmetry is broken here. This is the top view of MOS2. The two atoms are different here. The inversion symmetry is broken. Therefore, the opposite spins are locked to this momentum value. This K and K prime becomes distinguishable in MOS2. In the graphene lattice, in a single layer crystalline graphene lattice, all the atoms are that of carbon, and therefore K and K prime are not distinguishable in graphene. So this K and K prime, or K and minus K, can play the role of zeros and ones in electronics, and therefore it can be used to store, encode, and process information. And also you can see in the band structure plot here, opposite spins are locked to these momentum values. So first of all, you would need to generate carriers in these values. How you would do that? That is by using light of appropriate polarization. Like you need a left circularly polarized light to populate this plus K value, and a right circularly polarized light to generate carriers in this minus K value. Then, like in Hall effect, when experimentally you study Hall effect, you need to turn on the electric field, and then the carriers in this valley, they experience an effective magnetic field in K space, which is due to an intrinsic property of the material having a broken inversion symmetry and spin orbit coupling. So that is the Perry curvature. And higher the spin orbit coupling, usually higher is the Perry curvature and higher the valley polarization. So this is a V cross V kind of a term here. So the carriers in this valley, upon the application of the in-plane electric field, they acquire a transverse, this anomalous transverse velocity, and the carriers in this valley, they undergo a Hall effect, and which is called the anomalous or the Valley Hall effect. And very few materials are experimentally known which exhibit the Valley Hall effect. I mean, those materials are mainly MOS2-like, which show a large Zeeman type spin splitting at the valence band and a very small splitting at the conduction band. So since this is an emerging field of research, in order to facilitate the development of this area, we have contributed a few monolayers. We have proposed a few 2D materials which show properties complementary to that of MS2. So this is our little contribution to this area, and I'll be mainly focusing on these two papers, these two works in this talk. So this HFN2 monolayer was predicted using the particle swarm optimization technique as implemented in Calypso, but we have explored the valleytronic properties in this material. It shows a large Zeeman type valley spin splitting at the conduction band edge, which is complementary to that of MOS2. It shows a large splitting at the valence band. Now, if you replace sulfur by tellurium, if you replace sulfur by a heavier element, that is tellurium, the spin orbit coupling will be higher, and as a result of which the splitting will also be higher in this case. So when HFN2 monolayer is stacked on top of a molybdenum telluride, so to form a van der Waals hetero bilayer, a type 2 band alignment arises in it. So as a result of which, we are able to realize a large Zeeman type valley spin splitting at both the conduction band and the valence band. So this will be ideally suitable for valleytronics applications, because in van der Waals hetero bilayer, I mean, so one can prolong the lifetime of valley polarized excitons. So I will talk about the type 2 band alignment in the next few slides. So then moving on, we have also proposed these monolayers for the integration of valleytronics with spintronics. This niobium nitride monolayer or tantalum nitride monolayer, they have a hexagonal honeycomb lattice and a polar buckled structure. Because of the polar buckled structure, an outer plane electric field intrinsically arises in it, and which induces momentum dependent spin splitting, these out of plane electric field, and that gives rise to a Rashba constant. This is the Rashba constant is quantified by this parameter, and higher the Rashba constant, it is better for spintronics application. So for a material which is having a high Rashba constant, that is suitable for applications in spintronics where spin degrees of freedom are utilized. And also it has a large spin orbit coupling, and the inversion symmetry is broken, and therefore it shows a high Berry curvature which is much higher than several two-dimensional materials. So this shows also a reasonably good Rashba constant, and therefore we propose that these monolayers will be suitable for the integration of valleytronics with spintronics. And also what we find here is that these 2D materials are stretchable and flexible. They have a low elastic stiffness constant, and therefore it is worthwhile studying the response in the material properties to the application of mechanical strain. That is what we have done over here. Under the application of mechanical tensile strain, what happens is that the band gap is reduced, so which increases the Berry curvature, and the effect of the compressive strain is just the opposite. And also what we can observe over here is that niobium nitride it has a smaller band gap and therefore a higher Berry curvature as compared to MOS2. Okay, it's time to switch the gear to flexible piezo spintronics. The next generation channel semiconductor demands a seamless merger of these properties. It needs to show a large Rashba constant or a high spin orbit coupling and a high and a out of plane piezoelectricity, so that the external gate voltage source can be replaced by the intrinsic piezo potential under the application of external pressure or strain. And then low dimensional materials are by default, they have a low elastic stiffness constant, and so therefore they are flexible and stretchable. Such a pointer was given in this ACS Nano paper by the group of Dettelbaum on one-dimensional zinc oxide nanowires, and we have extended this concept to two-dimensional materials. So we have proposed a couple of monolayers which show a combination, which exhibit a combination of all these three properties, like ZNT and CTT monolayers. They have a polar buckled structure and a hexagonal honeycomb lattice as well. And because of this structure, polar buckled structure, I have been mentioning to you that intrinsically an out-of-plane electric field arises, which induces momentum dependent spin splitting in the conduction band, as you can see. So one parabola, it splits into two parabola. This is the momentum dependent spin splitting, and this is the Rashba constant. And you need a high Rashba constant for spintronics application. And also we are aware that spin orbit coupling is proportional to Z to the power 4. So cadmium is heavier than zinc, so therefore it shows a larger Rashba constant. And also because of the broken inversion symmetry, and out of plane electric field arises in them in CTT and ZNT. Likewise, the same thing is observed, the same thing applies to MGT. So in summary, these three monolayers show a combination of all these three properties. They show a low elastic stiffness constant, so this criteria is satisfied, and they have a high rush per constant and out of phase piezoelectricity electric coefficient. Therefore, we propose that these monolayers will be suitable for the for flexible piezo spintronics. And our findings and similar findings we have summarized, we have compiled and reviewed in this article, in this invited topical review, which I was asked to invited to contribute last year. So it's time to switch the gear to van der Waals heterostructures. And van der Waals heterostructures have mainly been explored, have mainly been studied in light harvesting applications, for example, in photovoltaics and in photocatalysis. Because of the type 2 band alignment, the electron hole pairs can be spatially separated out in the two individual monolayers. And now, as Professor Pandey mentioned in the morning, interface-driven properties were overlooked. Say, for example, so if piezoelectricity which might arise from the interface effects or from the interfacial polarization, that was completely overlooked until, piezoelectricity in van der Waals heterostructures were completely overlooked until we predicted it for the first time in this paper. And we have an evidence to substantiate the claim, and kindly bear with me, I'll show the evidence in the next few slides. So what Manish did that is that he designed this van der Waals hetero bilayer consisting of a single layer of boron monophosphide stacked on top of gallium nitride monolayer. And these monolayers are very close in the lattice constant, and therefore computationally it is not demanding to handle such calculations. And experimentally also these graphitic nanosheets, they exist, so therefore it is of experimental relevance. And now these individual monolayers, they only show in-plane piezoelectricity, they do not show any out-of-plane piezoelectricity until when one is stacked on top of the other. When one is stacked on top of the other to form a van der Waals heterostructure, and out-of-plane piezoelectricity arises, which is sensitive to the stacking order. And in this stacking order, when the layers are in perfect registry with one another, the interface dipoles are perfectly oriented along the z direction, the highest level of out-of-plane piezoelectricity arises in it. And then we have ascertained the origin of this out-of-plane piezoelectricity. It owes its origin to the difference in the electrostatic potential between the individual monolayers. The negative gradient of this potential builds up an electric field along the z direction, out-of-plane electric field, which polarizes the electronic cloud on the van der Waals heterobilayer, which is evident from this oscillations in the deformation charge density, alternating spatial regions of charge accumulation and charge depletion. So then we have tested our understanding on other systems. The understanding which is reached here, whether it is generally applicable to other van der Waals heterobilayer. So what we have done is that we have replaced gallium nitride by a monolayer which is similar to gallium nitride, close in the lattice constant to boron monophosphide and gallium nitride. So that's what we have done here. We have replaced gallium nitride by MOS2, molybdenum disulfide, and we find that our understanding is reinforced in this van der Waals heterobilayer as well. And here what we find, again, interface-driven properties. So if the two monolayers, when they are subject to a vertical compressive strain, there's a four-fold enhancement in the out-of-plane piezoelectricity. Now, moving on. So now Janus structures have been experimentally synthesized. So MOS-SE has been experimentally grown, synthesized. So what if we replace MOS2 by MOS-SE? So if we introduce a mild out-of-plane polarization in one of the individual monolayers, we find that there is a five-fold enhancement in the out-of-plane piezoelectric coefficient, and which has been confirmed experimentally on a similar system. So in summary, these are the first theoretical predictions on the occurrence of out-of-plane piezoelectricity in van der Waals heterobilayer, which has been on a similar system, and they have cited our papers, and that's how we have come to know. And also in this review article, they have newly acknowledged us. Piezoelectricity in van der Waals heterostructures was first predicted by Mohanta et al. Manish Mohanta happens to be my former PhD student. And our work on Janus structures have also been discussed in this review article. So now we usually calculate the piezoelectric coefficients. Experimentally, we measure the piezoelectric coefficients, but we usually ignore the sign of the piezoelectric coefficients. The sign of the piezoelectric coefficients can be important from even from fundamental perspectives. So we have ascertained the origin of the negative piezoelectric coefficient. We find that it arises from a small out of plane elastic stiffness constant. In van der Waals heterobilayers, you have a small out of plane elastic stiffness constant. So that gives rise to a negative out of plane piezoelectricity. That is what we find over here. And these monolayers, they show a nearly free electron gas states having a parabolic dispersion similar to that of graphene. This arises from the image potential surface states as in graphene. And when in this van der Waals heterobilayer, this is when the electric field is applied along plus Z or minus Z direction, either along this or this direction, these NFED states, they reach the Fermi level and enhance the electrical conductivity. When plus electric field is applied along the plus Z direction, the red bands of Na2T move upward when relative to that of the blue bands of CS2S, and when negative electric field is applied, the band movement is opposite. And now the closing and the opening of the band gap in the presence and absence of electric field, this thing can be utilized in digital electronics. And now coming to van der Waals solids, non-van der Waals solids, non-van der Waals solids. Normal solids are non-van der Waals solids, right? And the normal solids are much more abundant than the van der Waals solid. Normal solids are more abundant than the van der Waals solids such as graphite or MOS2, and the usage and applications of the normal solids or non-van der Waals solids are much higher than that of the van der Waals solids. And also, recently, experimentally, a few layers of normal solids have been exfoliated, and the success in the experimental exfoliation of a few layers of a normal solid has stimulated a surge in research interests in non-van der Waals solid. So here, these scandium nictide monolayers, they are stable in the woodlite phase in the bulk structure. So computationally, we have exfoliated a single layer of scandium nictide, and we have optimized it. It is found to be stable and having a hexagonal honeycomb lattice structure, and it shows a very small Young's modulus, so therefore it is super flexible. And then we have explored several other properties in scandium nictide monolayers. So usually V16, this is V16, I think this is not okay. The clarity in the pictures, okay. V16 is the shear piezoelectric coefficients. These are normally overlooked and ignored in two-dimensional materials, and they are usually studied in helical structures such as DNA nucleobases. And interestingly, this monolayers, they show a shear piezoelectricity. Shear piezoelectricity is like this. If you apply a torsion, a shear about the Z direction, polarization is induced along the X direction. Right? And so under the application of biaxial strain, we find that there is a complex mixing of these three phonon modes. They are most sensitive to the application of strain. The other strain mode, the other phonon modes are relatively insensitive to the application of strain. And that is what is understood to enhance the piezoelectric, the shear piezoelectric coefficient in these monolayers. And so the systematic variation is observed with piezoelectric coefficient D16 with the application of biaxial strain. And under the application of biaxial strain, the piezoelectric coefficient D16 exceeds that of beta glycine molecule, which shows the highest D16. And if we pay attention to the top of the valence band, we find a heavy hole band and a light hole band. So now the in-plane orbitals constitute the light hole band, this, and the out of plane, the nearly flat bands arise from the out of plane orbitals. So therefore, if strain is applied, the hybridization between the out of plane orbitals gets reduced, so the bandwidth is reduced, so therefore strain flattens the bands further. That's what we understand from here. Okay. So moving on.
Professor Sakar, another 3 minutes.
3 minutes.
Yeah, please.
So as I mentioned, serendipitously we have come across an ohmic contact in this van der Waals heterobilayer. I mean, materials that we study are finally utilized in devices, therefore it is very important to understand the device properties. And occurrence of ohmic contacts are rare and uncommon, and serendipitously we have found it in this van der Waals heterobilayer when MPS is stacked on top of graphene. That means when the Schottky barrier is 0. So now the nature of the OV contact, whether it is an N-type OV contact or a P-type OV contact, is found to be sensitive to the stacking sequence, whether the chalcogen atoms face graphene or the magnesium atoms face graphene, because this is the band alignment in the absolute vacuum scale, and when the interface is formed, when the van der Waals heterobial layer is formed, the potential step is different. It varies from one to the other because the interfacial polarization varies from one stacking sequence to the other. So in the end, we get an N-type OV contact in this stacking sequence and a P-type in this case. And then we have also opened the band gap in graphene by the application of vertical compressive strain. This has relevance to Professor Pandey's talk in the morning. So when the two layers are brought closer to one another, what happens is that there is a strong hybridization to the SPZ and CPZ orbitals. And when you are going past the equilibrium distance of separation, so there's a strong Coulomb repulsion. So a cumulative effect of these two factors facilitates the opening of the band gap. The band gap which is opened is much higher than the ones reported earlier. And also, apart from the pursuit of our independent theoretical research, we also collaborate with experimentalists and we provide them with strong theoretical support on different research areas, like this is catalysis, this is luminescence in atomic clusters, 2D materials, and so on, light harvesting, and so on. And hope I'm able to finish on time. Thank you for your. I skipped this in the interest of time, and since I'm standing between you and the lunch, I skipped this. And thank you for your kind attention.
I'm really sorry to stop you there. I know that you have a lot of data and lot more to discuss with the audience, but the thing is that we have the time limitation. But still, I will open the all part, one or two quick questions.
I'm just, if you can again give us your overall view, because I noticed for DP, this is a lattice matched piezoelectricity. So lattice matching is really essential requirement, or one can.
So for the calculation to be less
Yeah,
computation,
that's fine, but I'm talking physics wise.
Yeah, physics-wise. Physics-wise, the lattice match is not important actually.
So this is one of the.
It's not
The
the
second thing is, I noticed for D33, I think DP-MOS2, with the strain, it really collapses.
Yes.
So any physical insight is.
Yeah, then we calculated this anisotropy. Some anisotropy indices we have calculated because the piezoelectric coefficients are also related to the elastic stiffness constant. Higher the anisotropy index, higher is the piezoelectricity. At 5% of strain, the anisotropy index that drops down. That's the reason it collapses.
Any other question, please? So no question. Please join me in thanking Professor Sarkar for the brilliant lecture.
I take the question.
Okay, yeah, sure. Sorry.
We are doing research work in gens to the EMDS materials, and we have taken transition metal niobium and tantalum with sulfur, selenium, or lead. I have found in bulk material there is metallic properties we have found. We are trying to make semiconducting or half metallicity. So we have made monolayer also. So is monolayer will be sufficient to give half metallicity or semiconducting materials, or we have to substitute elements. Which types of elements we have to substitute?
That is you see, in the bulk it is metallic. What is the material you mentioned? Can you please
NBSES.
NBSE?
Yes.
NBSE. So NBS2, you have made a Jana structure of NBS2.
Yeah.
In the bulk, in the monolayer phase.
Yeah.
Actually, the monolayer is metallic or is it half metallic? What is the
We
monolayer?
haven't tried, but we are trying to substitute with iron like this. Some materials. We haven't found, we are trying it. Just we have found supercell like 2x2.
But NBS2 residue is metallic, as I understand. You want to make it half metallic.
We are trying
To make it half metallic.
Yeah.
With selenium, you have tried. With tellurium also, you can try. It would be difficult, I guess, with tellurium.
Yeah.
Or with pnictides or halogens also, you can give it a try. Let's see which one works. It's hard to predict. We can do a calculation, electronic structure calculations, and then we can see which one will work. That can save the time and
If we use LLM,
yes.
then it meet the Rasabi effect.
We will what effect?
It follow the Rasabi effect or Zanus properties.
Rashtra effect.
Yeah.
If there is an out, yes, it will induce an out of plane electric field actually. If it is a Jana structure, and that will help to induce the Rashtra effect.
Okay. We will
It
try
has to
and
be
we will.
semiconducting as well.
Okay, sir. Thank you.
Thank you.
Okay, any other question, please? Yeah.
Actually, we are not till now, but 2D material is coming in all respect, like sensors and others. So my question is, as you are talking about that type 2 quantum oil, so type 2 quantum oil, so where there is a band offset is there. And although the electron and holes are in that, like in different well condition, that means they are already separated. So scattering is already reduced. So in that case, I think the mobility will be very much higher in that case. But it is like 1D mobility now, or it is the jumping or a kind of mobility.
You are talking
Like
about
quasi-2D.
type 2 quantum well.
That type 2 quantum you have shown.
Type 2 van der Waals heterobilayer I have shown. The electrons are in one layer, holes are in the other layer.
Other layer. Now their motion, if we have extracted or any transport we require, then in which direction? It will be one-dimensional motion.
Two-dimensional, because the electron, suppose it is in this 2D layer, so the electron mobility will be specific to the mobility of this layer, and the hole is in the other layer, so the mobility will be of that layer.
So that layer in the direction of plane, or if it is perpendicular, maybe for the thickness, it will be like in different state. Quantum mobility. That I am asking.
Because in the z direction you do not have any dispersion actually. The dispersion is only in the xy plane. So mobility will be in the xy plane.
But in z direction, you will be getting a kind of energy level because the thickness is very thin.
Right.
So we will be getting a kind of hopping kind of mobility or that
Very
kind
small
of
mobility along the z direction. I would expect mobility only along
only in the
in plane only.
Any other question, please? I think everybody is feeling hungry. So, but we still have one presentation of 10 minutes, oral presentation.
For the oral presentation, I would like to invite V.S. Bhushan, Assistant Professor of IIT Allahabad. So please come to the stage. So please wait a moment. I would also like to present a memento to our honorable speaker.
much needed yourself.
Very good afternoon. I'm Dr. Shanti Bhushan, and the topic about which I'm going to talk today is quantum capacitance in near valency doped steady nanosheets or asymmetric supercapacitors. To talk about the introduction, to talk about supercapacitor is an energy storage device, and it combines the good attributes of both the battery and the capacitor. If you look at a battery, it offers high energy storage, but its charge and discharge process is very, very slow. But if you look at a capacitor, its charging and discharging happens very quickly, but the energy storage capacity is very low. And the supercapacitor combines the positive attributes of both these. It offers a good energy storage capacity and rapid charge discharging ability. And the application of the supercapacitors, the supercapacitor usually preferred in the places wherever we require the rapid burst of power, such as camera flashes, or wherever we don't need regular maintenance, we require less maintenance, such as space applications. However, supercapacitors, they also have one issue, which is the energy storage capacity. So in comparison to normal capacitors, energy storage capacity is high, but when we compare it the same with batteries, its energy storage capacity is quite low. If we look at the lithium-ion battery, the energy storage density is 120 to 170 watt-hour per kg. For nickel metal hydride is 40 to 100. For lead acid battery it is 20 to 35, but for supercapacitor it is 5 to 10 watt-hour per kg. So this research, by using computational means, it aims at increasing the energy storage capacity of the supercapacitor by enhancing the quantum capacitance of the electrodes. By enhancing the quantum capacitance, we can enhance the specific capacitance. By enhancing the specific capacitance, we can enhance the energy storage capacity or energy density. Coming to the calculation mechanism, the quantum capacitance can be calculated using few mathematical expressions. So that first we need the density of states data, which can be extracted using the density function theory tools. After extracting the density of states data, we have to do some MATLAB programming, or we can use any other programming. So we can use also C programming or MATLAB. And here I have used the MATLAB programming. And this is the expression for the charge density, and D of E is the density of states, F of E is the Fermi-Dirac distribution function, and this is the Fermi-Dirac distribution function with respect to the applied potentials. And after differentiating the charge density with respect to the applied potential, we get the differential quantum capacitance, and after integrating the differential quantum capacitance with respect to the applied potential, we get the integrated quantum capacitance, and this integrated quantum capacitance it matches very well with the experimental report. First, we have verified the same for the pristine graphene. For pristine graphene, the red curve is the experimental quantum capacitance, and the black curve is the computational quantum capacitance, and they are in very good agreement. And after verifying the process, I moved to stenine. I have taken stenine. First, I have analyzed the pristine stenine. And in pristine stenine, first we have extracted the density of states, and we have confirmed that stenine also offers zero band gap, just like graphene. But the PDOS, it shows there are S states and B states. If you look at graphene, we know specific S states for pristine graphene because of the sp2 hybridization. But in stenine, we are having both P states and S states, and the presence of P states indicates there is sp3 hybridization also, and the report says stenine is sp2 sp3 coexistent hybridization. And this is the quantum capacitance curve for pristine stenine, and the charge storage curve also. The quantum capacitance offered by the pristine stenine is around 77 microfarad per centimeter square, which is about 7 times higher than the pristine graphene. So stenine offering around 7 times higher quantum capacitance than graphene. To explore different ways of enhancing the quantum capacitance of stenine further, we have introduced this vacancy defect in stenine. After introducing the vacancy defect, we have found that the band gap is still 0, but the quantum capacitance, yes, it increased very much. The new quantum capacitance is approximately 120 microfarad per centimeter square. Earlier it was 77. In the vacancy defect, it increased the quantum capacitance to 120 microfarads. However, when we have seen the formation energy, the stability it is compromised, and the formation energy shows the formation energy is positive here. It means the structure is unstable. So to increase the stability and to improve the quantum capacitance, we positioned the near valency dopants, indium and antimony at the SV site. At the SV site, we have placed indium and antimony. And positioning the indium and antimony has improved the stability. We can see the negative value of the formation energy here. And the quantum capacitance also increased very much. It is 116 microfarads per centimeter square in comparison to pristine stenine of 77. Similarly, for antimony, it is 107. To further study the same, further study the different mechanisms, we have introduced these near valency dopants, indium and antimony at the sp edges, single vacancy edges. So initially, one indium is positioned at the single vacancy edge of the vacancy edges. Thereafter, two indium atom dopants are positioned at the sp edges. Thereafter, three indium atoms are positioned at the sp edges. And similarly, the antimony dopants also positioned at the sp edges. And we have seen that as we are positioning more number of dopants at the sp edges, the stability is increasing. This can be attributed to the elimination of dangling bonds by positioning these dopant atoms. And we have observed that the antimony offers better thermodynamic stability in comparison to indium in staining, because when we position antimony, the antimony can offer a lone pair, but indium it cannot offer a lone pair. So we think this is the reason we are getting better stability for antimony in comparison to indium. And all these indium antimony dopants, they are offering the quantum capacitance on the positive side of the electrochemical window. And this says all these dopant structures, they are suitable for the anode electrode of the asymmetric supercapacitor rather than the symmetric supercapacitor, because quantum capacitance peaks are observed on the one side only. So we can say that these are suitable for anode of asymmetric supercapacitor. And so this is the data we can see here. When we do one indium and when we do one antimony, the antimony is offering better thermodynamic stability than indium. Similarly, when we do two indium and two antimony, the two antimony is offering better thermodynamic stability. Similarly, when we are doing three antimony, we are getting better thermodynamic stability. And the antimony, it is offering better thermodynamic stability, and it is also offering better quantum capacitance in comparison to indium. So we can say in staining, antimony is a better dopant in comparison to indium. And since these are near valence, antimony is a near valence dopant, there will be less thermodynamic, less lattice distortion as well. And next we have studied the co-doping of indium and antimony in staining, and we have positioned this indium and antimony simultaneously in the staining at different locations, at the SV edges, single vacancy edges, and at the normal sheet also. And we have found that still these co-doped structures are also suitable for the anode electrode of asymmetric supercapacitor, because the quantum capacitance peaks are available on the positive side of the electrochemical window. And looking at the stability data and the quantum capacitance data, the quantum capacitance peaks are lower in comparison to the individual dopants. And when we dope the individual dopants at the sp edges, we are having better quantum capacitance. But when we are co-doping, the indium and antimony, the quantum capacitance peaks are less. So we can say co-doping, instead of co-doping, it's better to go with the antimony doping in staining. Yes, this is the conclusion. So the conclusion says staining, it offers 7 times higher quantum capacitance than graphene, and antimony is a better dopant in comparison to indium, and co-doping is not that much suitable, or may not be advantageous. These are the references, and thank you.
Thank you, Mr. Swaminathan. Thank you for the very good lecture. So, if any question, please. Yeah, Professor Khalid. Yeah, madam, please.
So two questions actually. One is that did you do dipole correction when you were doing vacancy calculations?
No, sorry.
Dipole corrections? Dipole correction. Second is that you have a very definite kind of arrangement of atom doping around the vacancy. Experimentally, how one can realize that? No, how one can realize that? You don't know, but how
We are studying the two possibilities because experimental conditions it can go in any possibility. So in simulation we are doing all the possibilities. So if the experimental is analysis of positioning of data, then we have that is why we are doing all the possibilities.
So you say co-doping didn't do anything. So what is the physics behind it? What does co-doping do?
Maybe it's like in the choice of dopant is like near valence. So when we are using the group free atom, if we convert the semi into p type, then we use the n type atom, it will charge the semi into n type. But when we are positioning both p type and n type, maybe there is some neutrality.
Sorry, any other question, please? So no question. So I think it is time to go for lunch. But before I go for lunch, I have one question for Mr. Swaminathan. In your lecture, you generally mentioned that the agreement it was very good. But my point is that when you see it in a general statement, so when you give such kind of statement, it's better to give quantitative. How much is the percentage? It is 5%, 2%, 3%. And the second thing is when you do the experiment, take into consideration the uncertainty that is there in measuring the various instruments, using the various instruments. Because many times what happened that somebody says that my efficiency is 42%. Okay, and then the literature it is 40%. So that means he said that I have improved the system because my efficiency is 2%. In practical, he is right. But the thing is, nobody takes into consideration the uncertainty in the measurement of the various, this parameter using various instruments. So these 2 points I would like to take into your consideration. Thank you. Okay, so once again, I thank all the audience, and I would like to thank all the speakers for their brilliant lectures. So now I invite the organizer if he has to say something.
I request everyone to kindly proceed for the lunch. We will meet again after 30 minutes. Thank you so much for your kind attention.